Hello, everyone. We're glad you could join us. My name is Todd from CASI headquarters. We're here with April from CASI headquarters and Chris Hayball from the from the Toronto branch of CASI, who's hosting this meeting tonight. And without further ado, we will hand it over to Chris.
Thanks, Todd. Good evening, everybody. Thanks very much for joining us for our April CASI Toronto branch meeting. We've got an excellent presentation for you tonight, so glad to see a good audience here. As usual for these virtual presentations, I'll introduce the speaker and they'll take it away. And we'll entertain questions at the end. So if you have a question, please write it down in the chat window, and then we'll gather them up and answer them at the end of the presentation. So we all know that the aviation industry, and particularly the airline industry, has been hit very hard by the pandemic. But tonight's presentation is about a very neat project that should help to get the airlines moving again in this new world that we now live in. Our guest speaker is one of the collaborators on this project, and I'm very proud to be able to introduce him as one of my colleagues at de Havilland. Thineshan Kathirchelvan is a senior engineering specialist at de Havilland, Canada, specializing in acoustics and vibration. Thineshan graduated in 2013 from the Engineering Science Aerospace option at the University of Toronto. He completed a 16-month internship at Acoustics Engineering Limited, where he was exposed to auditorium and room acoustics, HVAC noise, and building and train vibration. His thesis on shape optimization of acoustic reflectors in auditoriums gathered the interest of the acoustic community due to its novelty, as he was able to fuse concepts from both the aerospace and the auditorium acoustics fields. At de Havilland, Canada, Thineshan works on cabin noise, community noise, and the vibration environment on the Dash 8 series of aircraft. Prior to joining de Havilland, Canada in 2019, he worked at Bombardier Aerospace on several developmental and sustaining aircraft programs. His main interest lies in experimental acoustics and vibration, and he has contributed to research and development projects on various programs to help develop novel technologies for noise and vibration reduction. With the onset of the pandemic, he developed an interest in pursuing disease transmission dynamics in air travel, and he's focused on projects that could mitigate the impact of the pandemic on the aviation industry. Thineshan is obviously fascinated by sound, so it's not surprising that when he's not studying noise, he loves listening to music. In his spare time, he also enjoys bouldering, snorkeling, and hiking, and he's extremely enthusiastic and optimistic to be able to travel again. The first item on his list is to complete his scuba diving open water course somewhere where the water is warm. So, warm welcome from CASI to you, Thineshan. The floor is yours.
Hey, thanks so much, Chris. It's a very good introduction. Thanks for that. So I will share my screen and we'll get right into the presentation. Should be able to see my screen now. And okay, perfect. Everyone can, or Chris, if you can confirm, you can see the screen.
Yep, looks good.
Perfect. Okay. All right. Well, thanks so much for having me here at CASI. I'm excited to present this a UVC disinfection methodology for the aviation industry on behalf of the entire team that worked on this project at de Havilland and Aerohygienics. And I thought this picture, this came in from our give me one second. Okay, this came in from our industrial designer this morning, and I thought it was appropriate given it's Earth Day. So happy Earth Day, and we'll get right into the presentation. On the agenda today, we have basically, 4 items that we've sort of divvied up here. So we have the conventional methodology, so trying to understand what was available to our operators and airlines when the pandemic started, the fundamentals of UVC, why this technology could pave the way for the future, aircraft material compatibility study, and lastly, we'll get into the the highlight of this presentation, which is the actual solution and the development and testing that went into that. So starting with conventional methodology. So basically at the onset of the pandemic, aircraft operators increased the frequency of aircraft cabin disinfection manyfold. So operators employed a combination of chemical wiping, electrostatic chemical spraying, and chemical fogging to disinfect the surfaces of the aircraft after each flight. And an operator survey revealed basically several issues faced by the worldwide community. And it was evident that disinfection required innovation and extension for the aviation industry as well. So that being said, this is basically some highlights from the operator survey we conducted in the beginning of, basically from March to June, July timeframe. And I'll just highlight a few questions here. This is basically a ranking of the most significant issues faced by the operators of our aircraft to the least when it comes to what was available to them as a disinfection means. So the first on the list was disinfectant material, the chemical consumable itself. It was hard to come by, it was unavailable, and there's a few other issues with that that we'll talk about later on. Human safety during product application, turnaround time. So in between flights, you're now interrupting that to do a deep disinfection. So that was an issue for sure. Increased labor cost associated with disinfection on top of the cleaning that was already there. And concerns about interior deterioration and maintenance as well. So the next question was, do you see the need for frequency of disinfection increasing, moving forward during the pandemic and beyond that? And the answer was, most of them said yes to that. And we, asked if there was interest in using UVC as an alternative, whether to completely replace chemical disinfectants or supplement chemical disinfectants to drastically reduce the amount of usage. And 75% to or unanimously many agreed that that would be a good solution. And a few other questions related to setting the stage for welcoming passengers back. So as regional operators, as a regional aircraft manufacturer and airline, we have to do more to start the travel wave again, because domestic travel will start ahead of international travel for the most part. So in that respect, UVC was seen as a marketable and a tool for current and future needs for aircraft disinfection, and that was unanimously agreed as that being a yes. So if we sort of summarize the survey takeaway, as well as conversations we've had following the survey with many airlines, you can basically categorize the issues related to chemical disinfection into 5 buckets. So you have the human safety aspect of it. So the need to ventilate the aircraft, which is already a small space. And when it's unpowered, there's no ventilation. Protecting people's skin, eyes during the disinfection process. So that was an issue. The second one is disinfection material and consistency. So the availability of consumables, region-specific product approval. So a particular product may be approved in Germany, but may not be approved in France. And the requirement for multiple types of chemicals for each type of material that is found on the aircraft. So seats may require something entirely different from thermoplastics, and the in-flight entertainment screen and Lexan and things like that. And the other problem with manual application of disinfectants is really inconsistency of application. The third item was material deterioration, and this, obviously concerns us. So degradation, some of the reports, 2 months into this pandemic, back when we conducted the survey, there was reports of degradation of painted markings and placards, some reports of faded leather, and operators kind of entirely avoided disinfecting certain parts of the aircraft because the material just wasn't compatible with the product that was available to them, or any product. So the windows, the IFE, the seats are sometimes avoided to safeguard the material. And the flight deck, obviously there's some delicate instrumentation in there that requires more focused concentration and treatment in order to make sure that that's not disrupted. The fourth item is turnaround time. So chemicals require, depending on the chemicals, it could require up to 10 minutes of dwell time. So what I mean by dwell time is the actual amount of time that a chemical has to stay in its liquid form or close to liquid form in order for it to be effective. And post application, it does require up to 30 minutes of aeration. So the amount of time it requires to evaporate for that liquid to evaporate and leave the cabin. So in total, there's quite a bit of time that gets added in between turnaround time that makes it impractical for disinfection between flights, although it was done. And lastly, obviously, the cost implications. So chemical consumables, electrostatic sprayers, and foggers, they are obviously expensive, and it was actually quite surprising how expensive they were and how much our operator costs have gone up due to the increased disinfection frequency. There's added labor beyond the standard cleaning. So, you've hired someone for cleaning, but now they also have to disinfect. So you need to equip them with PPE, training, all of that adds to the cost. So beyond that, there was a FAA Special Airworthiness Information Bulletin that was also released, and where they, talked about the impact of chemical disinfectants on the aircraft. And just a small quote here: too frequent, and please, you can review the full SAIB here. But too frequent or improper application could result in negative impacts, including corrosion, embrittlement, increased flammability, and electrical short circuits. So a lot of caution against this, and for operators to inspect with this in mind as the disinfection was increased. FAA did not comment on UVC in the SAIB when it was released, but stated that it is being investigated. And added that in the absence of data, caution must be exercised when it comes to any method of disinfection, including UVC. Right, so that's a short summary of what our operators were facing. There was a lot of panic. They were stranded when this all started. And so we started researching into other means of disinfection, and we started to focus on UVC, given its sort of superiority against other types of disinfection. So we'll get into a little bit of the fundamentals. So the context: sun emits heat, visible light, and UV, and a whole host of other frequency electromagnetic radiation. UVC is basically the spectrum of electromagnetic radiation that has a wavelength between 200 and 280 nanometers. So the sun's UVC, so obviously the heat enters our atmosphere, the light enters the atmosphere, UVA, UVB enters our atmosphere. UVC is actually filtered at the uppermost layer of the atmosphere, so it doesn't penetrate to Earth. And this is what allows organisms to thrive, because UVC does have a germicidal property to it. And that's what we're going to capitalize on in this solution. You can see a small graph here that's superimposed, but basically the germicidal effect of it peaks at 264 nanometers. There's recent research that is showing that there's a secondary peak at 212 20 nanometers-ish, and that's where you will hear about far UVC and things like that. But we'll focus on the predominant peak here. And for ease of reproduction, more than anything, the standard frequency or wavelength that is used is 254 nanometers. And that's what the lamps are basically emitting. Okay, so that's the context. The germicidal fundamentals, it's just a quick illustration, but here you have RNA. We're all now familiar with mRNA vaccines and things like that. So the RNA strand that's shown here, this is prior to a conceptual UV exposure. And what you'll see in this graph is RNA absorption peaks at the 260 nanometer. The lamps emit 254, so you get pretty good absorption of energy by these RNA at 254 nanometers. When this energy is absorbed, something has to happen to the energy. In this case, you get photochemical damage to the nucleic acid that these pathogens are coated with. And when that happens, it's no longer able to replicate and perform its function. Okay, and that's how the pathogenic inactivation is achieved. So this is all great. Before we go into some of the research that's available on the germicidal property and testing, I just wanted to introduce a few terms here, which is going to be important throughout the course of the presentation. So irradiance, so this is really the measure of the amount of UVC light hitting a unit area in a unit time. So this is basically how bright the light source is, as an analogy. Fluence is basically the measure of the total amount of UVC energy hitting a unit area. So take the irradiance multiplied by the amount of time of that particular surface being exposed, and that's how you get fluence, or the total energy that surface is being hit with. So it's F is basically equal to I times time. Okay. And the inverse square law is the relationship between irradiance and distance. So if you double the distance from the source to a surface, you get a reduction by 4 times in the irradiance. Right. So UVC was first discovered back in 1878, and it basically showed that you're able to sterilize bacteria exposed to this frequency. I'm not sure if it was accidental or not, but that's when this journey started. Since then, there have been a number of publications and research over the last many decades on various pathogens and the associated amount of energy you need to inactivate or get a log reduction. So when I say log reduction, log 1 is basically a 90% reduction in the concentration of that particular pathogen. Log 2 is 99, log 3 is 99.9, and log 4 is 99.99, and so on. So what IUVA has done, the International Ultraviolet Association, they've compiled the research and vetted some of that paper, the publications, and assemble these charts that show how much dosage you need for each kind of virus or bacteria or protozoa, which I haven't shown here, would need to be disinfected. So there's a lot of strong scientific backing. And at the time when we were doing the research, around the summer timeframe of last year, there was nothing done on the SARS-CoV-2 virus in particular. But given the amount of research that has been done, there's nothing special about the virus in its ability to not to withstand UVC radiation compared to many more stringent or more resistant bacteria. So in fact, the viruses are actually a little bit more easier to kill or inactivate compared to bacteria because of their softer protective barrier. So back in November, there was a preprint from Boston University on testing that was done on the SARS-CoV-2 virus. And I did reach out to Dr. Griffiths that was leading that research. So it was a preprint back then, but January of this year, it has been peer reviewed and published in Nature Scientific Reports. And these are basically some highlights from the paper. The sources here, so you're more than welcome to go and read about it. It's very good, concise experimental work. So the study was conducted in a BSL-4 lab at the National Emerging Infectious Diseases Lab at Boston University. The study basically administered a starting viral titer onto a glass surface. Each specimen was then exposed to a constant irradiance. So again, what we just discussed, the intensity of UVC of 0.849 milliwatts per centimeter squared. And then the time was varied to achieve a total fluence ranging from 0.68 to 7.64. And the goal was really to see at what fluence you get that non-detectable amount of SARS-CoV-2. So the study focused on identifying fluence required, and it concluded that the concentration of SARS-CoV-2 virus reduced below detectable levels in as few as 9 seconds for wet virus and 4 seconds for dried virus. And what this all means is it translates to a lethal 254 nanometer fluence for SARS-CoV-2. And to my knowledge, this is probably the first documented lethal fluence for the virus of 3.40 millijoules per centimeter squared to 7.64 millijoules per centimeter squared for the wet virus. Okay, so that's the summary, and this is really the documented proof that SARS-CoV-2 does react and UVC is effective against the threat in front of us today. Right. So with that sort of out of the way, let's go first into aircraft material compatibility testing. And this is where we, de Havilland was able to basically contribute to this work on the material compatibility testing. We had great support from our supplier, who I'll introduce in the next section. So we'll go right to that. So before the work started, we did some background research and basically found out that UVC is expected to only permeate micrometers into the surface of the material. Therefore, the impact on strength is expected to be benign. And the source for this is ASHRAE. A benign assessment in the building engineering world may or may not translate to the same in the aerospace application, because we use inherently different types of materials. We use thermoplastics, we use different kinds of leather and fabric. And also in our application, sometimes there's more stringency compared to the wall of a building or an office space, for example, a table, for example. And then at the same time, there was little to no data in the literature, especially on aircraft material compatibility to UVC, including thermoplastics, leather, and fabrics. And just to echo FAA SAIB, use caution with any method of disinfection, and this is exactly what we wanted to do. So we started a test campaign and wanted to fill an essential gap in literature on the impact of UVC on aircraft materials. And was intended to provide firsthand experience to our engineering and certification team to be comfortable enough to allow the use of UVC repeatedly, frequently on our aircraft interiors. The test matrix, we had 6 test points or test types that we were particularly interested in. At the core of each one of these tests, we basically had the UVC exposure at 254 nanometers for the equivalent of many, many thousands of disinfection in real life equivalents. And once that exposition was done, we subjected the material to 6 kinds of testing. So we did a thermoplastic tensile strength, and the goal of this was to determine if there was any loss in tensile strength of thermoplastics found in aircraft. Stress cracking. So this was done to determine if there was any surface cracking exhibited in thermoplastic materials. So after the exposure, the materials are repeatedly flexed to see if there's any cracking or something like that, artifacts being noticed on the surface. Third test point is flammability, and this was to determine if there was any effect of UVC exposure on the flame propagation properties of thermoplastics and leather. Number 4 is appearance. So although this is not an airworthiness concern, we wanted to make sure that there's determine what the changes were in the look and feel of the material during the exposure process. Number 5 is transmissibility, so determining if UVC can permeate through the window of the aircraft, and you'll see why this is important later on. And lastly, given the intricate stitching on a seat belt, just wanted to make sure that the strength of the seat belt is not impacted for occupant safety reasons. This is the test setup, and this was put together by Aerohygienics that supported us quite a bit with this exposure process. So I'll sort of go from right to left here. So actually, just randomly, we have 2 UVC lamps. This is the source, and this is the same lamps that's going to be used on the product that we will be introducing. An aluminum side panel allows for reflection. So aluminum is one of the it's like a white wall, but for UVC, it's highly reflective. So this helps to distribute and make the test bed as even as possible. So that's the aluminum side panel. There's a UVC receptor here, which is very hard to see in this picture, but there's a receptor here that measures the irradiance, real-time irradiance. There's also a UVC meter, and again, it's blocked by my iPhone here, but you can see the UVC meter on the iPhone screen. And then we had a Microsoft Teams stream set up to continuously stream the whole test campaign, where we could have DADs and other engineers sort of witness, the testing. Especially the start, the stops and things like that. You'll notice here as an example, there's 4 materials that are put on the bed. And a UVC enclosure basically helps to block UVC light. So you can see the blue glow, that's just the visible light component from the lamps, but UVC does not leak out of the enclosure. So this allows us to test the materials inside. So this will be the exposed material, whatever's baking inside, and what's sticking out, this will be used for control for the various tests. So for each set, so we divided the exposure into 5 different sets, and it spanned from December 20th all the way to the early part of February. And each set basically had 3 things that was done to it. So the first one was prior to starting each set, a UVC grid irradiance measurement. The next step was actually exposing the material to a certain amount of fluence. And lastly, a material property test. And we'll get to some details for each one of these. So the test procedure encompassed firstly the grid irradiance. So this is to determine the spatial irradiance on the test bed. And then you'll notice here there's a red reference measurement. So this was based after the grid irradiance test was done. We used the receptor position at the reference measurement to continuously monitor the UVC irradiance, and then just used a transfer matrix to convert the reference measurement to each one of these points. But before the test, we measured each one of the points to determine what the distribution of irradiance was. And this really allowed us to zone in and choose a section of the test bed that minimizes the standard deviation of irradiance, which ensures that all parts of the material received a uniform amount of cumulative fluence. Okay, we've talked about this before. So most of the sets of exposure, depending on the stringency that's needed. So if it's an airworthiness related item like flammability or tensile strength, stress cracking, things like that, we would expose it to as high of a dosage as possible. And I would argue that this exposure is probably, reaches levels that no one else in the industry has done. And the reason for that is not because we wanted to, hit a high number. It's just given our regional operation, if we're doing 5 to 8 flights a day, and to disinfect in between each flight, that's quite a number of disinfections. So we really pulled it to very, very high amounts of disinfection to translate into a high number of disinfections in service. It's just an example of the material placement on the UVC exposure bed. And you'll see here, there's 4 materials, top of my head, Boltron, Ultim, Royalite, Aeroform, just few classes. And this was repeated 5 times with different materials and different sizes of materials to get a big array of materials in the end. You'll notice these control strips, and the goal of this was to test in parallel to the end goal for these materials, which was to do the tensile pull test. We also wanted to check the appearance evolution with UVC. So at every 50 joules, so in this case, we took it up to 700 joules, but every 50 joules, we would put a blocking strip to prevent further exposure to UVC. And in this way, you get a picture that's frozen in the amount of UVC to determine where the appearance actually starts to change. Right, so we'll go into test results. So when it comes to the thermoplastic tensile strength, no impact on that property due to UVC exposure. Stress cracking, again, the flexing, so no impact on stress cracking as well. This is the vertical burn test that was done on the coupons, no impact on flammability. And for appearance, we determined that we can make an assessment of negligible to slight discoloration of some materials after an equivalent of 5,000 heavy disinfection doses. And this translates to many years in service. No change to feel or texture. And when it comes to transmissibility, just to talk about this a little bit and why it's important, when we're disinfecting an aircraft, we want to disinfect both the window shade as well as the window dust pane that is just behind the window shade. So when you lift up the window shade and do the disinfection, you want to make sure that the UVC does not leak out of that first layer, although there's 2 other layers. There's 2 acrylic layers beyond that forms the pressurized vessel. Want to make sure that it doesn't penetrate beyond the first layer, and that was shown to be the case. There is no transmittance beyond the window dust pane, so you can disinfect, with and without the shades open. And then for the seat belt pull test, it's a small setup picture here. No impact on tensile strength due to UVC exposure as well. Okay. With all that out of the way, I really want to get into the most interesting and the final product that our customers and airlines and operators would benefit from, and obviously the flying public. And so we'll talk about UVC disinfection in our last section of the presentation here. So prior to getting into that, I do want to introduce our suppliers. These guys are the heroes of the show here and what we're doing here. So Aerohygienics, SME, stand for subject matter expert or small medium enterprise. It's applicable. Both are applicable. So Aerohygienics is a company based in Ottawa. They're fully in charge of the design and manufacturing of the unit. And the corporate team is comprised of aviation enthusiasts with decades of experience in the industry. And the advisory board comprises of epidemiologists and UVC scientists that recommended certain design parameters and requirements, and have been consulted throughout the development. When Aerohygienics was introduced to us, they had already developed a prototype of the robot. So, we didn't start from scratch. It was a much bigger robot, and it was tailored really for the wide body applications. But us being a regional aircraft, we wanted to collaborate to customize something for narrow body and wide and regional aircraft. Us as an OEM, so de Havilland Canada designs and manufactures the Dash 8 series of aircraft. In this collaboration, we provided design support and operator facilitation. The knowledge of various interior configurations through our interior and advanced design functions was applied here. We had material testing and certification capabilities through our interior and material engineering and DAO functions. And that was predominantly used in the section that we just discussed. Introduction and marketing to operators through our in-service engineering and marketing sales functions. And so we have experts that understand what the operators need and what's important, so that we can tailor the solution so that it's accessible by our customers. And finally, an aircraft level testing and approval as an OEM. So de Havilland Canada was introduced to Aerohygienics by Transport Canada Civil Aviation through our delegates. So with that handshake, the primary task, we agreed to collaborate, and the primary task at hand were to miniaturize the design substantially to optimize the design for Dash 8, other regional and narrow body aircraft, conduct aircraft material compatibility testing to ensure UVC is safe for use on aircraft, and perform aircraft level testing to optimize autonomous operation. So this was our timeline. So basically started when we heard the panic in a technical steering committee call from our operators on conventional disinfection methodologies. So that's really where we introduced the UVC disinfection in concept to determine if there's any interest at all. We then conducted the survey that you've seen. We then released some service letter because there was a lot of products out there, wands and stuff you can order on Amazon. So we wanted to provide some guidance based on the research that we conducted. So we released a service letter to our operators so that they can go out and find a solution that works and it's safe and approved. But following that, we had a bunch of operator inquiries requesting whether requesting whether de Havilland is working on a solution or trying to help operators find a solution so that they don't have to go out and find this on their own. And this is where we were introduced to Aerohygienics back in October of 2020. And so the remaining activity was basically all done in 4 to 5 months since that introduction, and what you're about to see. So it was a extremely fast-paced research development and testing exercise. But we're happy with what we have now. Okay, so we're able to produce a novel disinfection technology in the span of a year. When we started this collaboration, we were obviously working very closely with Aerohygienics, but we also wanted to involve our operators and our airlines into the design phase itself. So, we didn't want to create a solution and say, okay, here you go. This is what we want you to use. But we actually invited them to participate and provide feedback on certain elements that they want the focus to be on, so that it's tailored for for the day-to-day operation for them. So we conducted a few tripartite workshops with Aerohygienics, de Havilland, and a number of our operators, and gathered, and our field service representatives as well, and gathered a bunch of feedback. Things like protecting the lamps. Obviously, they're lamps, so they have to be protected. Ease of loading, and you'll see why this is important for a regional operation. Maintainability has to be very easy to maintain, so we can't hold up an aircraft to maintain something on the product. Battery swap capability, so that you can continuously disinfect without having to take the product back for charging. Weather resistance, disinfection time, minimize disinfection time, and obviously cost was a big factor in our operator criteria. So that was also factored in. And hygienic stream, which was introduced by Aerohygienics to the operators, was also welcome. So we factored that into the design as well. So all of that created the product, and this is the product. So this is basically Aerohygienics has fondly given it a name. It's called Ray, so we won't call it. I won't call it a unit or a robot or a product. It will be called Ray going forward. This is basically a realistic render of the Ray in the Dash 8 400 cabin. Just some high-level attributes of Ray. It's a fully robotic application, so you'll notice it's there's nobody in the cabin, and this is the intended use. It's how we want it to be used on the aircraft. So it's fully robotic. It's a compact design, so it could fit in the narrow aisles of many regional and narrow body aircraft. Medical grade application, chemical and emission free, and we'll touch on this a little later. Environmentally friendly and quick turnaround times. So let's break the design down a little bit. So let's go to the primary design requirement. So when I'm saying currently, but when this started, chemical disinfection is performed by human applicators. With any outbreaks and pandemics, there's going to be it's going to be shortages of N95, and that's certainly what we saw. And other PP that is required to safely perform the disinfection function by the human applicators. UVC disinfection helps to substantially reduce or eliminate exposure of chemical disinfectants to aircraft, cleaners, and passengers. But as we mentioned before, UVC itself can be harmful to human beings. Therefore, the primary design requirement was to create a fully autonomous robotic disinfection scheme. And there was no compromises made on that. So with this, we get a few cool sensors here. One is a camera. The second one is a sonar. The camera is really for motion detection, situational awareness. So if anyone walks in inadvertently, and it's all controlled by our processes and aircraft maintenance manuals and things like that. But if anyone inadvertently walks in, it's able to detect and shut off the UVC. And the second item here is a sonar, which basically helps to, you can have sweaters and pillows that are sometimes left on the aisle that are not picked up by the cleaning crew. And if that's the case, the sonar is able to detect that and stop Ray before it goes and trips on it. But the real vision or intelligence is provided by a LiDAR on this face of Ray. And this basically allows it to have frontal and lateral vision, so that it's able to center itself between the seats and traverse the aisles. Okay, that's autonomy. Size compatibility. So we designed, when we set out on this, we didn't want to just create a solution for the Dash 8 aircraft. We wanted to design, there was no competitive advantage in doing that. So we wanted to design something that was that, at least in terms of dimensions, can fit within any regional or narrow body aircraft. So it's a very compact design, 12 inches in width, 26 inches in in depth or length, and 52 inches in height. And it was a simple mechanical design. There's no moving mechanical elements here. There's no extensions and arms, and that was all done to keep the design as simple and robust as possible. Ease of use, so simple touchpad for day-to-day use in order to avoid reliance on external devices like smartphones and tablets. So you don't want to sit there trying to connect to Ray, and or sometimes you don't have a tablet or the app on the tablet that you can use to connect. So wanted to also have a simple touchpad, so that was designed into Ray, and this allows cleaners to basically push a button to start disinfection. Dual vision. So we talked about one face of Ray. So let's call this the front face. The back face of Ray, if I just flip that, that's on the other side. All the sensors are basically mirrored on the other end. And this allows Ray to basically reverse without turning in the tight aisles of an aircraft. So you saw how narrow the aisles are. So it's impractical for Ray to turn around. So the back face basically has mirrored sensor, so it's able to see backwards when it's reversing. We didn't talk about the timer function, but there is a little bit of safety features here for UVC. So once the start button is pressed, a timer comes on, and this allows the cleaner or the handler of Ray to walk out of the aircraft, close the door or curtain, whatever that may be, and basically just sit there or stand there until the disinfection is done. There's also some safety features. We have an emergency push button, so if any time you need to manually interrupt Ray, you have to wear some face shield and PPE, but you can quickly go in and push the UVC power down button, which will kill the lamps instantaneously. And lastly, another safety feature is a switch, which basically disconnects electric power, hard disconnect to all the systems and lamps and motors and whatnot. So that's a hard kill switch. And this can be done, this can be used to transport Ray or move Ray, so it doesn't, loading and unloading. So Ray can be loaded via jet bridge. So we've all walked through that jet bridge on many aircraft. It can be loaded via the aft service door. But for us, the Ray was also designed to handle a critical load scenario for regional operation and some other operation where manual loading and unloading is required via the air stair door. So to illustrate that, that's what I mean by that. So in some cases, or in many cases, you would have to manually walk Ray up the air stair door. So it was designed and in its handle optimization. So the top handle, the handle for the person on the front side is as high as possible. So it's actually in the middle of Ray, just below the LiDAR. And the handle for the bottom person is as low as possible, so you don't have to use a lot of biceps to curl it up. And in this illustration, this is a little bit exaggerated, but it is a bit more of a relaxed holding when you take Ray in and out. The load weight of Ray is 63 pounds, and this allows it to be transported very easily with the two-person load, so 30 pounds, 30-ish pounds each, and can be used by male and female cleaners and operators in this configuration. Right. Once Ray is inside the aircraft, there's a quick single push latch access here, so there's no tools required. You just push this and the side cover comes off, and you could slide in the battery that you need. And once the battery is loaded, it's ready to go. So there's no tools required. And even with the battery loaded, we did strive to design Ray so that it can still meet the European regulation weight limit, workplace weight limit of less than 23 kilograms per person. So that's still adhered to, whether you take it in with the battery or not. That's still possible, but it's easier to take it without the battery. The second function of the single push latch access is swappability of batteries, so rapid battery swap to continuously disinfect with the single ray. And we wanted to avoid the corded electrical connection, so completely, because that improves maneuverability and independence of ray, and also allows for improved portability of ray. Powertrain, it's equipped with drive wheels on one end. This is what you see here, and casters on the other. When ray is powered, drive wheels are energized. So if ray needs to be positioned, slightly differently in the aircraft, the drive wheel can be, the side of the drive wheel can be lifted up so that you can push by the casters, or additionally, you can just disengage the safety switch to disengage the drive wheels, which will allow ray to be pushed and pulled by all four wheels. Right, lamp protection. So this was a big one. We had a lot of help from industrial design from the Havilland side, and a lot of good work from mechanical engineering and aerohygienics as well to really nail this down. So the primary function of cage is to protect the lamps, but when we conducted the workshops with our FSRs and operators, they identified, okay, what if someone actually pushes by the cage or pulls by the cage? So it ended up creating unintended use cases of the cage. So we had to basically design for it. So when you put something, if it's more accessible, people will push and pull by that. So that's really the the human factors aspect of it. We tried a lot of designs, as you can see here, and basically we found something that struck the right balance between function, unintended function, and aesthetics as well. And that's what you see here. So the final design was a simple yet sturdy skeleton that protects the bulb, but was also aesthetically in tune with the rest of the unit design. Ray can now be pushed, pulled by cage. Ray can also be supported by the cage during loading and unloading, lateral support. And you can see here the X retainer that's placed here. This is to prevent the bulbs from shaking and rattling. So it's a very sturdy, single unit. Not a lot of degree of freedom for the bulbs with this design, which is good for protecting the bulbs. The ray can be operated with the cage on. It does not hinder UVC transmission out of the unit, which is why the amount of obstruction has been minimized as much as possible. And it is easily removable for shipping and maintainability. So if this gets dinged during a load or unload scenario, you don't have to ship the whole unit back. You can just simply remove the cage, ship it back for repair, or get a new one and simply attach that on. Right, so with that being said, this is basically how ray is going to be used in the aircraft. So we call it dual pass methodology, but basically we have two passes of ray. So once ray is loaded into the front of the aircraft on the Dash 8 series of aircraft, the first thing that is done is ray is positioned against the forward lavatory door, with the lavatory door actually opened and held open by ray. So the lavatory door is spring loaded, so ray can easily hold on to that door because it's a light spring that's used on the door. The configuration is set for the first pass. So in this case, overhead bins are closed, meal trays are deployed, so in the open position, and window shades are down. And once that's done, the cleaner or handler of ray will go and walk out of the aircraft, close the door or close the curtain. And then that point, after 30 seconds, ray starts its motion. It goes very slowly, but pretty quickly to the back of the aircraft. I should say very consistently, but quickly goes to the back of the aircraft. And when it reaches the back galley, it shuts off the UVC lamps, and the operator is informed by visual cue or auditory cue or a notification. And at that point, the cleaner can walk in, reconfigure the aircraft. So overhead bins are now opened, meal trays are up, window shades are up, and it's in a passenger boarding. It's ready for passenger boarding. And at that point, you start Ray again, and you walk out of the aircraft, and Ray again consistently but quickly comes to the front of the aircraft, and shuts off the lamps, and disinfection is complete. So the total disinfection time, so this yellow path here takes about 2.5 minutes, and the blue path here takes another 2.5 minutes. So in total, we have 5 minutes, plus the reconfiguration time where a cleaner would have to come in and reconfigure for the second pass. The full duration of this disinfection, we talked about fluents, we talked about lethal fluents of SARS-CoV-2. The heavy disinfection mode of Ray, which takes the full 5 minutes, administers 5 times the 254 nanometer lethal fluents for SARS-CoV-2. So we saw a number like 5 to 7 on average, 5 milliwatts per or millijoules per centimeter squared, and Ray administers 5 times that to provide safety factor for real world application. And that's basically the dual pass methodology, and I don't think I'm missing anything here. Oh, once it's in the front lamp shut off, there's no aeration time required. So as soon as the lamps shut off, it's as if nothing happened in the cabin, except the pathogens are reduced or inactivated. And cleaners, passengers, they can board the aircraft as soon as the lamps are off and unloaded. That's it. I'll show a quick video, and you won't hear any audio here, but I'll talk to it. This was basically shot. It's an engineering test, so it's not a marketing video. So we just kind of shot it on iPhones and stuff, given the COVID situation we were going through at the time. But here you can see I push the start button. I walk out of the aircraft. You can see the lamps energizing. They come on. The lab door is held open by Ray. So at this point, it's actually disinfecting the lavatory. And as Ray moves, the lab door closes. And keep in mind, the cage is not in place here. It hasn't been installed yet. So you can see it walking to or moving, and that's the real speed of Ray. Moving to the back of the aircraft, gets to the back, and then starts going back to, so that's pass 1, and it goes to the front, and when it gets to the front, because the lab door is now closed, you disinfect the other side of the lavatory door and the flight deck door as well, and that's it. You walk into the aircraft at this point. Okay, and a couple more slides here. Hygienic stream. So what this is Ray is connected, with Wi-Fi and cellular chips to a network, a dashboard for the airline or operator. So they're able to monitor where Ray is. They're able to monitor which aircraft it's disinfected, when the last disinfection was, and all of that is centralized on a dashboard that operators can now use to monitor the sanitization status of the whole fleet. It's cloud reporting, and it also allows for predictive maintenance. So some information can be shipped to Air Hygienics and to Havilland to help with maintenance efforts and predict when certain things need to be changed, or if there's something not quite right with Ray, we can we can predict that before it happens and get in there and get it fixed. So that's hygienic stream for short. And the other thing this allows airlines to do, if they choose, is they can now broadcast when disinfection, when the aircraft that a passenger is going to board was disinfected. So if I check my check-in app, it would have a notification saying that ray and UVC disinfection was used prior to your boarding or something like that. And that really helps with passenger confidence and boosting their comfort, which matters a lot. Certification and in-service introduction. We have Air Hygienics has EPA approval, UL, and CSA approval for Ray. And our first launch customer that I can publicly announce to you is Hydro-Quebec. There's a few other operators in work, but it's not publicized yet. But we have Hydro-Quebec. And it is quite nice that we have a Toronto-based OEM, an Ottawa-based producer of novel disinfection methodology, and a Montreal-based operator. So that's yeah. So with that said, let me do a final slide here. So I'll bring back the picture. We'll talk about all the issues we had with that our airlines complained and brought to our attention. We were able to solve with this solution. So human safety, PPE is not required due to the autonomous operation. Cleaning staff not exposed to chemicals and UVC, and no ventilation is required after Ray does this thing. Disinfection consumables and consistency. So it's a chemical-free solution, does not emit ozone. So this was specifically a design criteria for the lamps. The lamps last many thousands of hours, which translates to many 10,000s of disinfection cycles, because each disinfection only takes about 5 minutes. Autonomous and consistent disinfection. So time after time, every disinfection is consistent. There's no error that comes with manual application of chemicals. Material deterioration. So we've demonstrated that it poses no airworthiness risk based on our testing. Turnaround time, it can disinfect the Dash 8 aircraft in 3 to 5 minutes. So our Dash 8 100 and 200 is 3 minutes, or 300 is 4 minutes, just due to the length of the aircraft, and 400 is 5 minutes. And it can disinfect other regional narrow body in under 8 minutes. Cost, significant short, medium, and long-term savings. So as I mentioned, we were surprised to find out how much money was being invested by airlines on chemicals to perform disinfection. So there's no chemical consumables, sprayers, or the need for PPE with this application. So cost dramatically goes down, and the return on investment is less than a year for Ray to take care of a certain section or subset of a fleet. So in addition to that, so this is what we talked about before. In addition to that, it's compact design. Easily removable battery allows Ray to be independent and can function basically anywhere. It improves portability, and it's interchangeable across many models of regional and narrow-body aircraft. And one thing I'll note here is you don't have to program Ray for a particular model of aircraft. It's just looking for a wall. So on an aircraft, obviously, there's a clear aisleway. It's an occupant safety requirement. So once Ray goes and encounters a wall, it pauses its UVC lamps, and that's how you know it's got to the end. So aircraft can get longer or shorter. There's no reprogramming needed. It's a sustainable solution. It's manufactured in Canada, mostly aluminum manufacturing, and highly recyclable, and no emission and environmentally friendly. And passenger confidence. So Hygienic Stream provides dashboard to operators to monitor disinfection. Airlines can communicate latest updates on disinfection to the public, to the flying public, which again is very important for comfort. You don't want people to be nervous when they're flying. Some people are already nervous flying. You don't want to add another element. So try to keep passenger confidence and comfort as high as possible. And that is all I have here. And with that said,
Thank you, Thineshan.
yeah,
That
okay.
was great. Big round of virtual applause for that presentation. Everybody at
Yeah,
home, please clap loudly.
no, and Chris, I do want to introduce. I'm just going through the attendee list here. I do want to introduce Aerohygienics here. So I think Chris, Peter, Arash, you're all here. Thank you so much. This is all your hard work. They're still working their backs off, trying to get this to airlines and operators, conducting training and getting the word out. So thanks for all the hard work that you've put into this, and thanks for letting me represent you guys in this presentation. And thanks for allowing me to be a part of this as well. It's highly appreciated.
And a welcome from CASI to the Aerohygienics folks who are on the presentation today. I was hoping that you'd be able to attend, so thanks for joining us. And if there's any questions that perhaps Thineshan wants to defer to you, you're certainly welcome to chime in and help to answer them. I've had briefings on this topic before at work. As I mentioned, Thineshan and I are co-workers. But it was great to see the whole thing in all its detail and with the video and everything. I really enjoyed that today. Thank you very much, Thineshan. I hope that everybody in the audience enjoyed that as well. What a cool project to work on, and obviously a great benefit to the airline industry. There's a number of questions here in the chat. Some of them have actually been answered in the course of the presentation. I'll just zip through those quickly, but there's a couple of other questions that certainly deserve an answer. So somebody commented, Peter commented, is the ray based on line of sight? Hence, how do blanked corners or other areas get disinfected?
Yeah,
And Gary asks, can you provide some idea of the impact of what could be called the shadow effect, i.e. mist surfaces not directly exposed, such as edges and backsides, not the ones that sit in the seats, presumably. John asks, will all folded tables be ignored and not be disinfected? And Alex chimes in, perhaps one can just unfold the tables. So with those questions partly answered in your presentation, Thineshan, is there anything else you'd like to say about little nooks and crannies that don't get reached, that sort of thing?
Yeah, for sure. Yeah, and this is, it's a common question. There's no 100% solution with any disinfection method. With our dual pass methodology, where we're doing 2 passes, with first pass where we have surfaces, folded, second pass where they're not folded, so stored versus deployed. This really helps to get as many surfaces as possible. We know angle is not a function, or the UVC intensity is not really a function of angle when distance is held constant, and we have CDC research showing that. So the angle at which the light hits an object, it's immaterial. So the energy has to go somewhere. In this case, the pathogen intercepts the energy, whether it's being hit at a 90-degree angle or a 5-degree angle to the surface. Nooks and crannies, under seats, the carpet under the seats, not too much of a concern there. Nobody really touches that space. So it's really about high touch surfaces. And when you actually, with the motion of ray, because it's always in motion, you're constantly changing the angle to the various surfaces to get as many surfaces as possible. But at this time, we only have confidence to say that it has to be a direct line of sight in order for this to be effective. So there will be some surfaces, we estimate around 5% of the surface area of the aircraft that would not be directly exposed to ray. And that's okay. Like I said, there's no 100% solution to anything.
Okay, here's a question from Blago. He says, since you mentioned there is currently little guidance on using UVC in aircraft cabins, are any updates or directives likely to come out of this initiative from the aviation authorities, Transport Canada or the FAA, regarding UVC being used for disinfecting aircraft cabins?
Yeah, we do foresee something coming out of FAA and most likely from Transport Canada as well. We don't have visibility on that. Again, airlines were kind of left to their own to determine what to do, and there was no real guidance on disinfection when this all started. So we did participate in RTCA EuroK committee and there is a standard available, DO 388. Which de Havilland and Aerohygienics contributed to. And we did put UVC disinfection and whatever we've learned throughout this test campaign in that standard. So that's available for anyone to go and use as a standard to apply this disinfection scheme. But only time will tell if FAA will produce enough data to provide some guidance. And again, that's why we ventured on this, because there was no data from Transport Canada, FAA. We have delegates within de Havilland that represent Transport Canada. So we did the test and convinced ourselves that this is not an airworthiness issue.
Okay, another question from Blago. He says, also, can this be used in the cockpit? Or is a different UVC product being developed due to the limited space?
Yeah, so the flight deck is actually quite interesting. We focused, our first priority was cabin. So again, getting that 80% solution rather than trying to do all at once. There's certainly some sensitive equipment in the flight deck that needs a closer look and more consideration. But we are very close to authorizing the use of Ray. So you simply, again, open the flight deck door, position Ray, and most of the knobs and control panels are in the direct line of sight of Ray. So that could certainly be done. We're in the midst of completing a few other checks to make sure that there's no other materials that we've left behind, particularly the windshield. We need to make sure that that's not impacted in any way. And if there's not enough data, the alternative is to put, simply block off the windshield. So many operators do have the aluminum shades that we have in cars for aircraft as well. So they would simply place that before application.
Okay, this isn't a question. It's kudos from one of the audience members. They say, this was amazing. Thank you, Thineshan, for a deeply fascinating deep dive. Thank you for making flying safer. I think we can all echo that comment.
Yeah,
another question. Sorry, go ahead.
No, thanks to the whole team. Honestly, it was really fun working with everyone at de Havilland. It was a small team, but it was a powerful team here at de Havilland and Aerohygienics. I've called them as late as 11 p.m. and as early as 4 a.m. Throughout this developmental process. So it was a blast, going through this experience.
Here's a question from Simon. Are you looking at marketing this for wide-body aircraft, that is, those with multiple aisles?
Interesting question. I don't know if Aerohygienics are able to unmute those. Can Chris or Peter chime in here?
I think everybody in the audience is on mute, so we'll have to unmute them.
Can you hear me now, Thineshan?
Yep, yeah, go for it, Chris.
Okay,
Welcome.
perfect. I can just hold down the space bar and actually override the mute. Firstly, I just want to echo what you had said, Thineshan. It was an absolute pleasure working with the team at de Havilland, and really nice to see the teams come together and ultimately the product come together. But to answer your question, I mean, Ray was designed initially, obviously, to meet all the requirements for the Dash 8, and Ray met all those requirements. But that's not to say it can't be used on other aircraft as well, including wide body, narrow body. Our intent right now, knowing turn times are very important. If we were to use it on a wide body today, what we suggest is you actually use two. You run one down one aisle and you run one down the other aisle in parallel. To keep those times very, very realistic.
Yeah, thanks so much, Chris. I wanted you to say that. I thought it was clever that we can use two ray on the wide body, something I hadn't thought about, when we spoke about it last, but wanted you to share that with the team. So yes, it can be used on a wide body. You just need two of them.
And I guess the inverse square law means that for a much wider cabin, with perhaps 3 seats between the aisle and the window rather than just 2, it won't have quite the same effect the farther it is away. That actually leads into the next question here. Somebody's asking, are window seats as well disinfected as the aisle seats?
Yes, they are. Yeah. So with the inverse square law, so yes, for wide body or wider narrow body, the speed of ray can be adjusted, so it can be slowed down slightly. Again, remembering that equation, radiance times time. So you just have to slow it down slightly to get to the further distance with the same amount of dosage. The window seats and aisle seats, yes, they are. So the calibration was done to the sidewall, which is the furthest distance away from ray. So that's where we've done the fivefold the fluence, 5 times the lethal fluence for SARS-CoV-2. So everything closer than that gets blasted. So we're okay.
So people who are carefully choosing their seat before they get on board, they don't have to worry about
No, don't worry
being
about
safer in an aisle than in a window seat.
Yeah.
Here's a question from Alex. How do you anticipate the use of Ray or similar autonomous robots to evolve in the future? Do you expect such systems to become fairly standardized even post-COVID?
Yeah, so the operator sentiment and there's a number of surveys done by many organizations. Disinfection is here to stay. It's not going to go away post-COVID. If anything, the frequency of disinfection may be reduced because we may not have to do disinfection after every flight, but disinfection is here to stay, at least on a nightly or 2 times a day basis. So with that, and that's really the goal, we wanted to make sure that we create a solution that is sustainable. We're not relying on chemicals and consumables as we move forward here. So this is really a short, we want to get out of the current threat. We also want to safeguard against future, basically block the transmission chain, disease transmission chain, in any way possible. So this is for now and for the future.
Here's a question from Andre. How many Ray do you expect to produce per month or per year?
I will redirect that question to Chris and Peter.
Hi, Thineshan, can you hear me again?
Yes, yeah, I got you.
Okay, perfect. Yeah, so right now, the question was how many per year? Is that what it was?
How many per month? How many per year?
How many do you expect to produce?
Yeah, I mean, the reality is there is no limit. We've actually are working with the manufacturer that actually produces all of our off-the-shelf parts and so forth. The way we've designed it, it's all about reproducibility. I mean, we can scale from 5 a month to 1,000 a month. There's really no limits on what we can do right now. It's really, really neat to see. We jokingly say we now have robots making robots to be able to manufacture that many at a time.
And hopefully the market is there. People will jump on board and actually purchase them.
Yes, we're hopeful of that too.
Do you think you'll have any competitors?
So we do have, there is one other competitor there right now. We do believe our product is superior in many ways. I won't get into all the details of why, but it's good to see competitors. I mean, if we're out there all alone, I'd be worried that you know, maybe we're off on a tangent in the wrong direction. But you know, it's nice to see competitors, and it's nice. You know, I think that allows us to challenge each other.
Oh, for sure. And yeah, anything novel like this, a novel application, you need competition to thrive and change the direction of the market as well, right? So you can't have aerohygienics as a lone warrior here. So we do need competition, and it's fully appreciated. But Ray looks pretty good.
Are there patents involved?
We do have a patent pending at this time.
Okay, here's another question from Blago. If they do become standardized, will you need to increase the fluence? And he also says, which virus is the hardest to eliminate? I think most people can relate to catching colds on airplanes. It would be nice not to worry about that again.
Yeah, so the fluence that we used, I think it's very generous. You know, it's 5 times what you need for SARS-CoV-2, and probably, you know, two times or two to 3 times what you need for more viruses and bacteria that are harder to kill. So I don't believe there's a need to increase the fluence, and this is at the sidewall distance. So the 5 times. So as you get closer and closer to Ray, the 5 times becomes, you know, 10 and 20 times. You know, if you're halfway between the surface, the sidewall and Ray. So don't believe there's a need to increase it. If anything, there's probably a need to have a light and a heavy disinfection mode. The light being something that would, you know, you can have half the lamps on, and that would help to save your battery power. So you can keep disinfecting for, you know, twice the number of cycles. So there's room for us to lower, but I think we're good on the high side.
And what about the comment about which viruses are hardest to eliminate?
Well, this is a hard question. I don't have all the names of the virus on the top of my head, so I can't comment on that. But do check out the link, the IUVA compilation, and you can see a list of all the viruses and bacteria. You know, you have so take a look at that, and you'll see most of the doses are within Ray's capability for kill.
Thineshan, you and I were talking about this yesterday at work, the use of UV for water purification, water disinfection. I'm just wondering if with this push to create Ray for the airline industry, if that might spur development of other UVC disinfection things for other types of germs and other types of applications, not just aircraft cabins.
Oh yeah, no, for sure. I mean, in fact, it started with water purification plants. I mean, that's where a lot of the UVC application was, but you know, I think it's mostly in Europe. I'm not sure if there's a lot of that in North America, but yeah, I mean, for sure, with this visibility, we hope it becomes standardized in many different sectors for disinfection.
Okay, there's no more questions here on the chat, but if somebody else has, oh, one just popped up. From John, will airports employ Ray for disinfection? Good idea.
Yeah, and I'll touch on this, but you know, Chris, Peter, feel free to chime in here. We're starting the issue is always, you know, for any kind of disinfectant application to be used, the first question is, okay, do you have the airline's approval? The second question is, you know, if you do have airline's approval, it has the OEM, so it has de Havilland or Boeing or Airbus, have they approved the methodology? So there's a series of questions and locks that needs to be unlocked when airlines adopt it. So we're targeting this, you know, obviously de Havilland is now convinced this is a good method for disinfection. So that's one lock that's out of the way. The next thing is to target the airline and have them adopt this technology. And when they do, airports can you know, start a service with Ray. and UVC disinfection to treat a whole bunch of different aircraft and airlines all at once. So yeah, for sure. There's really no limitation, or again, there's no competitive advantage to hoarding this for just de Havilland products and Dash 8. We want it to be as widely used as possible.
Here's an interesting question or comment from Simon. He says, this relates to your question regarding other applications. I have a Samsung UV cell phone sanitizer. Any comments?
I won't comment because I don't know what this is. Like I said, there's a lot of products out there, and again, the dose, the frequency of UV emission, UVC emission is all critical in its germicidal function. So without knowing what it is, I can't comment. But you have to do your research, make sure it's approved by certain organizations that provide some quality assurance to ensure that it can function as advertised.
Okay, I'm just seeing a comment here from Peter at Aerohygienics. Can you please unmute me?
Yes.
I see you in the list there, but I can't
No,
seem to unmute you.
I can unmute
Todd, can you help?
Peter. Hey, Peter, you should be unmuted now.
Yeah, thank you very much. No comments. I was just going to add something to your previous questions, and I think Chris took that on. Thank you.
Great. Thanks, Peter. And Peter's working very hard, trying to get this to the market. So thank you, Peter.
Another compliment for you in the chat there from Jeff. He says, great initiative and a great example of the confluence of the art, science, and business fostered by CASI. Most appreciated. Absolutely, I'll echo that.
Yeah, no, thank you, Jeff.
I don't see any more comments or questions in the chat here, so perhaps that's our cue that we're about at the end of our time here. I'll just make one comment that I was really fascinated by the fact that, I mean, we all know what UV does to our car interiors. For example, the sun visors rot in the sun, and the upholstery on the seat backs and the back window rot in the sun. And yet we're using that same physical property or similar physical property to disinfect the aircraft. So great that the material testing has shown that the fabric and so on is not susceptible. And of course, airworthiness considerations like strength and flammability and so on are check mark in the box too.
No, for sure. It's very, very important.
Okay, so I think we'll wrap it up then. Again, a big thank you, Thineshan, for sharing your evening with us and sharing your very exciting work that you've done that we've all enjoyed hearing about, and hopefully we'll all reap the benefits of, because we all travel on airplanes at some point. Thank you to the audience for joining us. At one point I saw 45 participants in the list. I'm not sure if that was the highest number, but that was a very gratifying turnout. Thank you everybody for joining us. I hope you enjoyed the talk. I can't tell you yet what our next CASI Toronto branch presentation will be, but watch out in your inbox. We'll tell you about it as soon as we can, and we hope that you'll join us for our next meeting. I can't say drive safely on your way home, but enjoy the rest of your evening. Thanks very much, and thank you again, Thineshan.
Yeah, no, thank you, and thanks for the opportunity. This is really great. Thanks.